Hello, good afternoon, and salam sejahtera, everyone. Thank you for joining me in this very last lecture of the seminar today. My name is Chai Hong from Malaysia. First of all, I'd like to thank the organizer for inviting me in this very important seminar. It's really a great pleasure to be here and meet every one of you. This is the topic of my presentation today, the science behind the art of UVC disinfection. These are the contents of my presentations. I will try my very best to give an overview on UVC within the coming 20 to 25 minutes. And I'm pretty sure most of you here are familiar with this diagram, the electromagnetic spectrum. From the very right to the left, we have non-ionizing radiation such as the radio wave, microwave, infrared, and ultraviolet, followed by ionizing radiation, X-ray, and gamma rays. So our today's topics focusing on ultraviolet. Many people may not be aware that the UV spectrum can be further divided into UVA, UVB, UVC, and Phi UVC. UVA and B have been categorized as non-ionizing radiation. But UVC and Phi UVC, they contain higher energy and they are categorized as ionizing radiation. And the naturally occurring UV is originated from the sunlight. UVA and B will reach the Earth, while UVC will be completely filtered out by the ozone layer. Let us now focus on UVC. UVC has a very important function. Scientists have found that UVC has strong germicidal effect, meaning that it can kill germs effectively, and the maximum bactericidal effect occurs at 240 to 280 nanometers. If you look at the dose response curve inside the spectrum here, the maximum germicidal effects happens at 264 nanometers, which is the wavelength of the UVC. So how UVC actually kills microorganisms? When microorganisms exposed to UVC in the range of 240 to 280 nanometer, it will be absorbed by the DNA, RNA, and the proteins. There might be two possibilities. Absorption by proteins will lead to rupture of cell walls and death of the organism. And if the UVC can go further into the DNA or the RNA of the microorganism, it will disrupt the replication process via a mechanism known as pyrimidine dimers, and the microorganisms are unable to reproduce themselves anymore. This diagram further illustrating the mechanism of action of UVC. First, the UVC radiation would break through the cell walls and reach the DNA and RNA. The UVC will damage the cell nucleic acid and protein structure through a process known as photodimerization, which causes two consecutive bases to bind together. And this genetic damage will prevent microorganisms from infecting and replicating, ultimately leading to cell inactivation. And lastly, we say the cell died when the microbe cannot infect or spread further. According to the FDA guidelines published just last year, the sensitivity of different types of microorganisms range from the bottom here, which is the least resistant to UVC, include lipids or medium-sized viruses, followed by vegetative bacteria, fungi, non-lipid or small viruses, mycobacteria, and finally bacterial spores. And the popular coronavirus COVID-19 belongs to the lipid group. Now let's look at how UVC is produced. As I mentioned earlier, the naturally occurring UVC will be filtered out by the ozone layer even before they enter the Earth. Therefore, all commercially available UVC are actually man-made source. There are several methods in producing UVC. I will mention the three popular methods here. The first method is known as low pressure, low intensity UVC lamps. Using this method, the UVC is produced by mercury at low vapor pressure inside a quartz tube. And this will produce essentially monochromatic UVC at 254.7 nanometers. Second method, using low pressure, high intensity UVC lamps. And mercury indium amalgam is used. This will allow 2 to 4 times greater UVC output and 25% greater lamp life. And the last method, using medium pressure, high intensity UVC lamps. And mercury vapor emission is carried out at higher lamp pressures and temperature. This will produce polychromatic UVC light. This graph shows the power distribution of the two different methods. The green spectrum shows the medium pressure lamp power distributions, and you can see they are polychromatic spectrums, so they have different wavelengths. Whereas the red narrow curve here showing the power distribution for the low pressure lamp. And comparing the two methods, the low pressure lamp is preferred because it produces a very unique wavelength and very close to the germicidal peak. Okay, let me explain it in more details. This diagram shows the low pressure lamp. The lamp contains mercury, which will vaporize when the lamp is lighted up. And the mercury atom will accelerate because of the electrical field in the discharge, and they will collide with the noble gas inside the tube and reaching an excited state. The excited mercury atoms emit almost 85% of their energy at 253.7 nanometer, and the remaining energy results in various other wavelengths, but mainly 185 nanometer. However, most UVC lamps used for disinfection applications are treated with an interior coating that prevents any vacuum UV, which is 200 nanometers and below, from being emitted from the lamp. And this is to prevent the production of ozone. If we're comparing a UVC lamp with a fluorescence lamp, you can see they have a very similar structures. Except in the fluorescence lamp, glass tube is used and it contains phosphor crystals. The glass tube will block the UVC radiations and allow only the visible light to transmit. Whereas in a UVC lamp, the quartz tube is used. Quartz tube will allow UVC light to transmit. And the quartz glass can be used to produce UV lamps either with 253.7 nanometer output or with both the 185 nanometer, which is far UVC, and 253.7 nanometers. This can be done by changing the transmission properties of the internal glass coatings. Next, let's look at the applications of UVC. UVC has a very strong history of proven defense against diseases. Started from 1878 to the early 19th century, there were first publications of the effectiveness of UVC against TB. And in fact, this discovery has won a Nobel Prize. And since then, the UVC was given the name as a germicidal light. And later on, UVC has been used in water and wastewater treatment. And this has been approved by the FDA and the US Environmental Protection Agency. In 2016 to 2018, there were 20 microbicidal and 12 hospital-associated infections reduction studies endorsed the use of UVC. And last year, the comprehensive IES has reported that UVC found to kill COVID-19. And also the Center of Diseases Control also recommends UVC as an effective disinfectant against COVID-19 mitigation. And here shows some examples of the use of UVC. The very first diagram here showing a fume hood, which is very popular in any microbiology labs. And we are always instructed to turn on the UVC lights for at least 15 minutes after we've done any microbe or viral related experiments. Then the food industry, they also use UVC light to kill bacteria or pathogens on the surface of the fruits to prolong the shelf life. And in water purifying industry as well, UVC has been used to kill the pathogens or bacteria. And after filtrations, the water can be drunk directly, even without boiling. The other very popular application is in aquarium or fish tank. UVC has been popular to be used to kill bacteria in the water and also to prevent the growth of algae. So in general, the application of UVC can be grouped into these four industries: food and liquid industries, waters, air disinfection, and surfaces disinfection. These are some examples of surface disinfection in rooms. This is our very own CT scanner room at the UMC. And this is a custom-made portable UVC lamp specifically designed to disinfect the CT gantry. And this low pressure, high output UVC lamp can actually be used for large space such as office, conference halls, even cinemas, operating theaters, schools, and etc. But the installation must be carefully planned to ensure every area is covered. And these are the examples of air disinfection, which is also a very popular trend at the moment, where the UVC is used to disinfect the air inside the room constantly. And to do so, we need to have an air circulation that passes through the UVC source. And for buildings or places who have centralized aircon, the UVC lamp can actually be installed in the HVAC room so that the return air will be disinfected before it's being supplied again to the buildings. And hopefully with these applications, it can help to prevent the spread of pathogens inside the buildings. Then we have UVC robots. So-called robot is basically a portable UVC systems that can move around over a large space area. But of course, sensors must be applied so that it doesn't expose human subjects when it's moving around. And now, especially during this COVID-19 pandemic, we have seen many creative use of UVC in the public areas. For example, the first diagram here shows an airport, and the tourists are disinfected in an enclosure before they're being used. And the next picture shows the handrail of the escalators is being disinfected, okay, using the UVC. And inside the aeroplane, the portable UVC system is used to disinfect the areas. And this one is even more amazing. This is implemented in China as well as in Japan. The buses, okay, after every shift, it will be disinfected in this very strong UVC disinfection setup room, externally and internally. And closer to us, in the healthcare setting, healthcare-associated infections, HAI, is not new. It remains as an important source of morbidity and mortality that leads to 1.7 million infections and 0.1 million deaths annually. The major source of nosocomial pathogens is thought to be patient's endogenous flora, meaning inside the patient's body. But an estimated 20 to 40% healthcare-associated infections have been attributed to cross-infection via the hands of the healthcare personnel, either from patient contact or indirectly from touching the contaminated surface. The poster shows here if you are admitted to a hospital, you have a 5% chance of contracting an HAI. This sounds scary enough, and therefore hospitals remain as the priority place for regular disinfection. So recently we've been using these terms a lot: sterilization and disinfection. And of course, this is two different terminology with different meanings. Sterilization is the process by which all forms of microbial life from surface, medium, or instruments are destroyed by various physical and chemical methods, such as radiation sterilization, heat sterilization, or even using chemicals such as the ethylene oxide. Whereas disinfection, meaning destructions of all pathogens or organisms capable of producing infections but not necessarily spore. All organisms might not be killed, but the number is reduced to a level that is no longer harmful to health. So as the term shows here, infections, okay, it is related to the human health. Okay, and disinfection simply means we stop the chain of infection. Well, we have covered most of the basics of UVC. Now let's talk about the advantages and disadvantages. The advantages of UVC disinfection, as I listed here. First, they are more effective than conventional disinfection methods, such as chlorine or using chemical disinfectants, in inactivating most viruses, spores, cysts, and etc. There is no residual toxicity, no chemical addition required, no formations of disinfection byproducts, no consumables required, is minimal operating cost and minimal maintenance. The UVC lamps have a long lifespan, usually more than 8,000 hours, and also a higher dosage than required for disinfection. UVC can be used to reduce the concentration of trace organic constituents of concerns such as NDMA. NDMA is a highly hepatotoxic and carcinogen in the laboratory's animals. And the disadvantages include no immediate measure of whether disinfection is successful. We cannot see it with our eyes. There is no instant measurement method. The UVC is harmful to the eyes and skin if exposed directly. There is currently no standardization in terms of the disinfection protocols worldwide. The effectiveness therefore varied by system and also the operating protocols. And the UVC has limited penetration, so it plainly just disinfect the surface which is in contact to the primary beam, to the direct beam. And we need professional knowledge, okay, in the applications. We need to provide training to the users, and also we need additional safety control such as the motion sensors, auto turn off functions when motion is detected, interlock system, and etc. And in comparison, it is relatively higher setup cost, but in long run it is more cost saving. Next, I would like to focus more on UVC dosimetry, as it's an important topic and it's the technical knowledge that we need to excel in if we want to apply UVC disinfection effectively. So the first formula here is irradiance multiplied time will give us the UVC dose. The unit for irradiance is watt per meter square multiplied time will give us in joule per meter square. And the UVC dose is depending on the type of microorganism and log reductions that we want to achieve. And the irradiance, meaning the intensity of the UVC radiation, is depending on the distance between the UVC source and the object surface. And here the inverse square law applied, meaning when the distance gets further away, the intensity of the UVC will reduce in a function of square. And what is log reduction? This is a formula. Log reduction equals to log A over B, or log A minus log B, where A is the number of viable microorganisms before the treatment, and B is the number of viable microorganisms after treatment. So log A over B will give us the log reduction value 1, meaning 90% of reductions of bacteria. The number 2, value 2, meaning 99% of reduction. Log 3, meaning 99.9%, and so on. And there are a lot of publications mentioning about the UVC dosage in order to kill different types of microorganisms. So this is one of them, one of the reference showing different types of bacteria and also the log reductions, 90% and 99%. So I take a common example here, which is the E. coli. It's a very common bacteria in a hospital setting. And to achieve 90% reduction of the bacteria, okay, which is log 1 reduction, we need at least 3000 microwatt second per cm square of the UVC dose. Okay, or this is equivalent to 3000 microjoule per cm square. And To achieve 99% reductions, we need 6,600 microjoule per cm square. And there's other guidelines from the International UV Association. So it gave a summary on germs that need minimum doses of 2 to 40 millijoule per cm square. For the yeast, we need at least 30 to 30 millijoule per cm square, and for fungus, we need higher doses, which is 50 to 400 millijoule per cm square. And the minimum UVC dose recommended by International UV Association to inactivate virus is 40 millijoule per cm square. And this should be used as a minimum UVC doses in order to inactivate viruses. Okay, let me show you an example here. This is for surface disinfection. The first step we need to do is to calculate the longest distance between the UVC source and the object surface. This is based on the known height and the fixture of 2 times 45-degree angle. So according to the trigonometry formula, once the longest distance is measured, we can apply this formula here to calculate the UVC energy at the point of measurement. And the second step, if the distance is known and the UVC power of the lamp is known, then we can calculate the required exposure time to achieve the dose that we want. Say, for example, at 1 meter away, and we know that the irradiance of the UVC is 10 milliwatts per cm square. This is given by the manufacturer. Multiplied time, we will get 40 millijoule per cm square. 40 millijoule per cm square is the minimum UVC doses recommended by the IUVA, and solving this equation, we'll get the time as 4 seconds. And this is at 1 meter away. Okay, what about at 2 meter away? Then the inverse square law will be applied. So basically, the time will also be doubled by a factor of 2 or square. So from 4 seconds to 16 seconds. And there can be another option where the distance and the preferred disinfection time is known. Then we can calculate the power of the lamp. And then we can determine how many UVC lamp that we want to install at that particular area. This will be depending on the luminaire performance, the number of luminaires and the lamps to be used to disinfect. And the distribution, the UVC dose distribution should be overlapped because as the UVC output will reduce fast when the distance increase. Alright, so that's the example of surface disinfection calculation. Now we move on to air disinfection. Say we have a UVGI unit, the upper room germicidal irradiation unit like this. Okay, the first step we need to do is to calculate the dimensions of the duct and the exposure time. So using this formula, ET is the exposure time, volume divided by Q. Q is the airflow in the unit of meter cube per second. So volume also equivalent to width multiplied height multiplied the length. And from there we can get the exposure time. And we can use this formula here, the second step. RR equals to 1 minus E negative KLM ET. RR means the removal rate. So we want to calculate how much is the reduction of the microorganism in this case. And we can fill in all the parameters here. ET already calculated. K is the UV rate constant in the unit of meter square per joule. And this one can also be referred to the guidelines. For example, by Walker 2007 for coronavirus. Okay, the constant, UV rate constant is 0.377. And LM is the mean irradiance. Okay, this one can be also obtained from the manufacturer specs. So from there, we can calculate what is the removal rate of bacteria if using this system. For UVGI system, there is a minimum requirement of 7 feet from the floor in order to prevent the direct UVC beam from reaching the occupants in the room. Okay, there's another important parameters in air disinfection calculation, which is ACH, meaning air change per hour. It's a metric to tell us how many times a HVAC device can fill up the full volume of a room with air. This is especially important in calculating UVC intensity for sufficient disinfection. So this is the formula. ACH equals to CFM multiplied by 60 divided by the area and the height of ceiling. ACH is air change per hour, CFM is cubic feet per minute. And to convert minutes to hour, we need to multiply 60 here. And this is the airflow rate. And it's depending on the fan speed. And it has been emphasized by the WHO and FDA that the air change rate is a vital measurement in the fight against COVID-19, as ventilation plays a very important role in reducing the infection rate of COVID-19. And there are many publications and guidelines from the regulatory bodies as well for the air change per hour for different building types. For example, here in a bakery, we need an air change at least 20 to 30 per hour. And for a conference room, 8 to 12. And for hospital clean room, it should be 15 to 25 air change per hour. So how do we measure UVC? Of course, there's a UVC sensor and a meter, and it needs to be calibrated, okay, to the wavelengths of the UVC. And also there are some instant UVC dose indicators available, but these are really very subjective measurements and is not really calibrated. Talking about the effectiveness of UVC, there are easily more than 10,000 papers available that documented the effectiveness of UVC in the inactivation of multiple types of microorganisms. Here I selected a few papers which are related to SARS-CoV virus. This is a review paper saying at 360 mJ per cm square, the SARS-CoV-1 had the highest UV lethal dose among 130 viruses from hundreds of published studies summarized by Kowalski. And this is one of the early published data on COVID-19 viruses, which was published in IEEE Spectrum last year. The top images here shows the COVID-19 viruses in the petri dish, and the lower picture shows more than 99.9% of the COVID-19 virus killed after about 10 minutes of UVC exposure. COVID-19 is a single-strand RNA virus, and in order to achieve 90% of viral reductions, we barely need 1.32 to 3.2 mJ per cm square of the UVC doses. This is another very popular paper in scientific reports. UVC irradiation is highly effective in inactivating SARS-CoV-2 replication, published early this year. The paper summarized that an UVC dose of just 3.7 mJ per cm square was sufficient to achieve more than 3 log inactivation of COVID-2 without any sign of viral replication. Moreover, a complete inactivation at all viral concentration was observed with 16.9 mJ per cm square. And also, there has been rapid development of far UVC since the starting of COVID-19 pandemic last year. This is another very popular paper in scientific reports documenting that far UVC efficiently and safely inactivates airborne human coronavirus. The study mentioning that continuous far UVC exposure in occupied public locations at the doses of 3 mJ per cm square per hour will result in 90% viral inactivation in 8 minutes, and so on. Another recent review of 80 papers on 1985 to 2020 mentioning that the efficacy of UV-based sanitizer technologies are promising, but are dependent on numerous environmental, physical, and technical factors. And the authors made a conclusion that the UV technology should not be utilized in isolation and should be considered as an adjunct to protocol-driven SOP. And there are various factors that can affect the effectiveness of UVC disinfection. Briefly, include wavelength of the UVC light, humidity of the environment, the surface materials, types of microorganisms involved, and UVC intensity, which can be affected by distance, tube cleanliness, and life hour, as well as the microshadowing issues. And lastly, I will talk about the biological effects of UVC and the protection measures. The absorption length of UVC in human skin is extremely short. Almost no UVC can reach the living cells in the skin. All the absorption occurs in the dead skin layer. Therefore, it is unlikely that UVC presents an acute or long-term hazard to human skin. However, UVC is likely to cause acute photokeratitis at the eye for short direct exposure to the naked eyes. An exposure limit for UV is 3 mJ per cm square as recommended by the EU Health Agency safety guidelines. And for personal protective equipment, UV goggles or the full face shields are recommended. In addition, cover any exposed skin using lab coats, nitrile gloves, or other lab attire. This is the maximum permissible time for UVC exposure, with constant irradiations to the intensity on the skin must be limited to 0.1 microwatt per cm square. And with an irradiation time of 8 hours a day, the maximum intensity must be limited to 0.5 microwatt per cm square. And similar to the practice in ionizing radiation, the UV hazard symbol must be displayed at the area where the UVC exposure is undergoing. And it is always recommended to add additional warning with more description. For example, UV radiation inside, no admittance without UV eye protection. That's the end of my presentation. Thank you very much for attention. If you have further questions or comments, feel free to email me at the email address here.